Okay. All right. So I'm going to start recording these lectures because we've had the wonderful privilege of having our initial couple COVID cases in the department. So you're going to start noticing some people missing. So as a reminder, the way this works is if you are sitting next to someone with COVID and they catch it, you get sent home as well, unless you're vaccinated. If you are vaccinated and you are sitting next to someone with COVID, you don't have to go home into quarantine. So one more reason to get vaccinated. Also, vaccines are becoming mandatory next semester anyways, so don't just do it unless you don't want to. Yeah, unless you don't want. We'll see how long that lasts. I expect it to actually become more mandatory as time goes on. Anyways, I'm going to be recording it. The recordings are not always the best, just because technology kind of sucks, but I will do my best to make sure that if you are stuck at home, you can still, participate and pass the class. All right, so that being said, there's, one other thing I want to mention. Something that I am working on, so I'm the club advisor for IEEE, so we're trying to make the club more engaged for everyone. One of the things that we're looking at doing is, you may have seen my IEEE shirt. It's the black one with the collar on it, and it says IEEE SSCS, which is the Solid State Circuit Society, which is like the big society for analog engineers. We're looking at doing one of those shirts here that will have a little Weaver logo and then say IEEE Club. It'll also be a nice black material with the collar. It's like something that you could wear to work. That's something we'll be selling likely. I think they're going to cost $20 to $25 when we do it, is what it looks like. So just kind of keep that in mind. Think about if it's something you'd want, because the way I'll do it is I'm going to set up some pre-orders, and if we get enough interest, I'll buy a bunch of them and I'll buy extras, but I'll use kind of the pre-order stuff to fund that availability. Also, we're looking at bringing back what we have is a snack bar that we usually set up in this IEEE lounge that's kind of been dead since COVID, but we might bring it back. I've secured funds to stock it. So that's something else to hopefully look forward to if things keep going the way I want them to. And we don't have a crazy another COVID outbreak and we have to go completely online, which would be a nightmare. All right, so today we're going to be talking about a couple of things. And what I want to start off with is reminding you about state machine diagrams, right, which we've talked about before. Did we talk about state machine tables, SM tables at all yet? Okay, great. I didn't think so, so it's fine. So we're gonna talk about three different ways actually to represent state machines in visualization. So the first thing that we're going to do is we're going to talk about the graph, the state machine graph or diagram. They're synonymous. And let's go ahead and just design a super simple state machine to detect 110. Let me do the different, so I just stick with my notes so I don't get lost. 101. So we just want to detect this. And remember, when I say detect, I mean assert a signal that is true if it sees that signal. This is going to be a serial detector. So this is coming in on your serial line, kind of like your UART, right? You plug this into the UART and kind of look for this. Reasons that you might want to do something like this is in like UART, there are certain characters that could cause the PC to like exit the terminal depending on your terminal program. So you may want to set a detector on your serial stream that's going out that says, if you see the sequence, abort kind of thing. But it's really just a simple example. So the state machine graph should be really easy for you guys, right? We're always going to start with some essentially idle state, where if we're going to draw this out in its entirety, it's going to have an enter, right? This is where we're coming from when the system turns on. We can call it S0, and then it makes a decision. If I get a 0, I don't do anything. I stay on idle, right? So if I have this continuous stream of zeros, nothing happens. Now, what I like to do anytime I'm planning out my state machine is plot out the path that is most important. So in a detector, it's the path that is a detection. So I can just do this, and I just look at the number of states, S1, S2. Now I know, and hopefully you know, that if it's a Mealy state machine, I need the number of states equal to the number of bits in my detection sequence. If it's a Moore state machine, I need that plus one number of states, right? Because a Moore state machine only depends upon which state you're in for its output. So I need a state just to assert the output. But I'm going to do this in a Mealy state machine since I've done Moore's previously. So what this says is if I see a 1, 0, and now I need to come out with a 1, I know this 1 is also going to assert my output Z. Where does it go? I do want overlapping. That's 1, correct. So if I get 1, 1, 0, 1, 0, 1, I'm going to get 2 detections, right? On the other hand, if I get a 0, I have no part in that. Now, if I wanted to write this out completely right, I would go through every single one of these and say that output is not Z, et cetera, et cetera. I'm generally not that picky, and I'm perfectly happy if you just write when it's true or what the output is, like this. Now, I write it this way because this doesn't depend on which state I'm in as much as which state I'm coming out of and what the input is, right? Whereas if I was a Moore state machine, I would do something like that. I'm not, I'm doing Mealy. Okay, this only needs one more part, which is if I go 1, 1, I stay put. Right, this is a state machine graph or diagram. This is generally how I will start, and this is how I tend to think in state machines. However, this is not always the best way to represent it, especially if you're trying to design the next state logic or the output decoder logic, right? So if we remember what a state machine looks like, it has 3 main components. It has current state, which is really just a register that stores your current state. It has the next state logic. Well, it looks at the inputs, I, we'll call this I, and outputs your next state. Now this is going to be some vector that has some number of bits equal to however many bits I need to represent all possible states, which will make more sense when I get to the next step. Then it also needs to consider what state am I currently in, right? So the next state is looking at where am I, for example, S1, and what is the input? If it's a 0, if I'm in S1 and a 0, I go to S2. That's my next state. Okay, that signal right here is your next state signal. This is going to be combinational logic. This is the output of that combinational logic. This then is your output decoder. In a Moore state machine, I'm done. That's the structure of it, where the output coder in a Moore state machine just looks at my current state and says, what are my outputs? In this case, I only have one output Z, but I could have potentially some number of outputs, right? It could be more than one, like in the stoplight example, right? I'm going to have a signal for every red, yellow, and green that's in the intersection. But I would need a different circuit for each one of those lights. Okay, now there is a little bit of a twist. If you remember, the output decoder in a Mealy state machine also considers the input. What that means is the input gets fed forward into the output decoder. So it looks at both current state, which is the signal, and current input. Now, it's important to recognize that if you've designed a Mealy, the Mealy state machine is actually going to assert the true signal, the Z, the detection, 1 clock cycle ahead of when a more state machine would do it. Right? Because I enter the state, the output coder says, oh, my current state has updated, my input has updated, therefore update Z. Whereas a more state machine has to wait until current state updates to next state, which would be an S3, and then it would go, okay, now I can assert that output. So you're actually going to be off by 1 clock cycle. And the output doesn't have to change at the rising edge of a clock, because it will change whenever the input changes. Right? As soon as the input changes with whatever logic delay there is, the output will change. That's what's going to change it. Okay. So why that's important is, let's say we're going along, and this is my clock cycle where I enter S2. And this, so that's clock. Then I have my input. If my input changes here from 0 to 1, because I was a 0 to come into the state, right? And now I'm 1, my output is going to change at the same point plus some delta, right? Where that delta is the combinational logic delay of the output decoder. Is anyone confused about that? Okay, good. Whereas a more state machine, this updates to S2, this updates to S3, that's where Z goes high. Mealy, more. Okay, well, let's go ahead and make this a little bit easier to represent as code, because this is not necessarily easy to represent as code until you've done it a couple of times. The way we do that is we create a table that simply says, let's look at what our current state is. Yeah, I'll do this way. Current state. What is our next state going to be based on what our current state is? And then what is our output? In which case, I'm just going to actually label it Z. Now, the current state has two different ways of being represented. One, the way we like to look at it, right? Where in the case of like your UART, it's going to say idle, right? That's your state name. But behind the scenes, it's binary. It's represented by zeros and ones. So if I say my current states are S0, S1, S2, these can be represented by 0, 0, 0, 1, and I'm going to start by saying 1, 1. Which implies that in here is another state 1, 0 that I'm not using, right? There's 4 bits, or 2 bits, 4 states. I only need 3 of them because it's a mealy. In a more, I would use all 4. Now, the next state, what does it map? What determines the next state? Well, look at the diagram, and we see that it is the input and the current state, because that's what this signal is. Okay? Next state, I want to determine based on I equals 0 or I equals 1. And I can say things like, well, if I'm in 0, 0, and I see a 0, I stay in 0, 0. Now I'm going to write this out as strictly the binary because it ends up with a neater table. In previous years, what I did is I would do this where I'd say S0, S1, right? Because if my input is 0, I say in S0. If my input is 1, I go to S1. This is fine, but then you have to go back in and fill in below it what that binary is going to be. And it ends up being a little bit messier table. Either way is fine. However you want to keep track is fine. But that's it, right? If I see a 0, I stay in state 0. If I see a 1, I go to the next state. If I'm in state S1 and I see a 1, I stay put. But if I see a 0, I'm going to state 2, which is 1, 1. Okay? Now, if I'm in S2 and I see a 1 here, then I go back to S1, which is 0, 1. And if I'm in state 2 and I see a 0, I go back to S0, which is 0, 0. Now, the last thing I have to do is my output. If this is a more state machine, my output is only determined by my current state. So I would just write one column. However, I have a mealy state machine, so I also need to consider the input, which is going to be I equals 0 or 1. And this is really easy part of the table because I can just look at it. The only place I have a 1 is if my current state is S2 and my input is a 1. Everything else is 0, right? Okay, this represents the same thing as this. But this one we can use to turn into the logic that corresponds to next state and output decoder. What tool do we have to create minimal logic expressions? K-maps. So the way we do that is, what are our inputs to the K-maps? Well, let's look at next state. Our inputs are I and CS, current state. Current state has 2 bits, so I can draw the K-map as follows, where C1 is bit 0 of current, or bit 1 of current state, and C0 is bit 0 of current state, right? And now it's just as simple as figuring out where this K-map gets filled in from, right? Well, if I'm at 0, 0, that's my current state of 0, 0, and an input of 0. So I'm looking at the bit. I can only generate one output. So in this case, my CS actually has 2 bits in it, the bus of 2 bits. So we need to solve both of them separately. So we're going to do this for NS, let's start with 0. So we're only going to consider the 0 bit of the next state. So this one is easy, right? Because it's 0, 0, 0. Now, if I want, what is 0, 0, 1? 0, 0, 1. 0th bit is a 1. 0, 1, 0. 0, 1, 0. I'm looking at my lower bit. That's a 1. 0, 1, 1 is also a 1. 1, 0 is state. Yes, don't care. I do not care what happens if I end up in that state because something bad happened. Now, when you've been writing your case statements for your state machines, a lot of times you'll write when others, right? And then define like idle. If something happens, go back to idle. In that case, it wouldn't be don't cares. They would both be zeros because we're trying to go back to S0. But right now, let's assume that we've designed our state machine right and we don't care. Well, the next thing that happens is the 1, 1, and we go 0, 1. Now, if we're able to go and solve that K-map really easily, right, we're going to have 4 here. To there. Do I need to cover that X? No, I don't, because I don't care if it's included in the logic equation. So then I can say, in the case of next state 0, I would say NS0 is equal to, well, this circle, the only thing that doesn't change is I. And this is going to be the sum of products expression, right? I, or this 0, 1 doesn't change, but I does. So, and this is current state, so C1 and C0, except for C1 is bar. So this is the logic that generates that bit. That bit is this signal. Okay? We can go do the same thing with NS1, which needs its own truth table. And now we know what's happening, we can fill this in really quickly, right? Where I can just go, well, it goes 0, 0, 1, 0. Don't care, 0, 0. And that one is simple. But there is something interesting that happens, because I chose arbitrarily, essentially, that this was going to be 1, 1 instead of 1, 0, right? Either one of those could be don't care. In fact, I could write them in any order. Now, there's this whole list of rules about how to order your state codes. However, I don't think I'm going to test on that this time. You might see a homework on it. If you see a homework question on it, just go look it up in the book. And basically, it says things that make a lot of sense, right? Is if one state transitions, if it goes from S1, S0 to S1, we want them to be adjacent logically in their state numbering. Why? Well, because it just turns out that it tends to put them closer to each other in the ones, right? However, this, I broke that rule, right? I'm not adjacent to either one of these. I kind of isolated it as not logically adjacent. So you can quickly imagine with me what would happen if I did the same K-map, and I'll do it with NS0. But instead, I just flip the state code. So the only thing that does is it flips these two, right? That's my K-map now. And so my simplification is 2 groupings of 4. I end up with 1 fewer signal in here, and it's just going to be I for C0. Right? So the order of my states directly impacts the complexity of my logic. Now that's like a true or false question I might throw on the exam is, can the order of the states impact the complexity of my OD logic? Or my NS logic, right? Yes, obviously, it just did. The same thing is going to happen for C1, for NS1, which is what this is. This is NS1. Because if I flip those two, this don't care ends up next to this one, and I get a simpler logic. Now my output decoder is the exact same thing, right? It's going to have the same input. It's going to care what is my current state and what is my input. K-map's going to look identical, right, for the setup, and then I just start filling it in. But I'm going to fill it in, you may notice, with a 0, 0, 0, 0, don't care, 0, 1. So there's 2 ways to handle this once you're a little experienced. If you're not experienced, you're going to go ahead and write, which I will have you guys do to make sure you understand it because it's simple. Or you can just look at it and know what it's going to be, because this one is that simple. However, take a moment, write out your K-map for Z. Create for me your output decoder logic. So that should be your K-map. And what you'll quickly recognize is the output decoder does not change complexity, regardless of which version I use, right? Because either way, you're going to end up with the same pairing, and you end up with the Z is equal to what doesn't change. Well, it's I and C, what I 1110 C1. Okay, everyone get that? Okay, so then I'll show you, I can generate that really quickly in my own head, because I look and say, well, the only time it's going to be 1 is when this current state is 1, 1. So I already know that it's going to be something like Z is equal to C1, C0, I. Well, I have this C0 that is extra, and I can recognize that this is kind of a tempting simplification to jump to and be like, oh, well, it's just an AND gate. But you notice how the only other situation where there's a 1 is in C1. What that means is I don't care what this is doing. Regardless of the condition that C0 is in, I can have a 1. So that's how I would just go, yeah, this doesn't matter. Okay, so something I would like to point out, because I think it shows up in the homework and it likely shows up in the exam, this was the simplest possible one. If I were to jump ahead and create an output decoder that asked for a sequence of 4, nothing really changes other than I lose the don't cares. My logic gets a little more complex. However, if I have 5 states, then I have to have 3 bits for my current state. So my K-map is going to end up looking something that was not 0 index, that's silly. 2, 1, 0. Like so, right? Now it's gotten more complicated. But that can show up. It's not that hard. I expect that you guys can do 4 variable K-maps. There's another version of this that could happen is, well, what if I have 4 states? So I'm going to need 2 bits, but I also have 2 different inputs. So instead of just the serial I, what if we were doing something like an adder, right? That is comparing 2 different inputs and generating an output. So in 2700, you certainly built a combinational adder. There's nothing that stops you from building a sequential adder. It's kind of silly, it's overly complicated, but you could do it. And then in that case, you have 2 inputs, A and B. Well, 3 if you're doing a full adder, but let's stick with 2. In that case, you have only 2 C1, C0 bits, but then you're going to have your inputs A and B. But it's the same thing, right? It's the same type of table. You're just comparing, instead of having I0 or I1, your table is going to look like that. And then you just fill this in based on what your I1 or AB, as I called it, I guess. But and so you'd be like, well, if my current state is 0, 0, and I'm going to call them A and B just for simplicity, and A and B are 0, 0. What is my next state? Well, it might be 0, 0. My stay put, right? That's all you're going to do is where do we go based on where we are. It's the same thing as the translation that we did for the state machine diagram earlier. It's just considering 2 inputs. Okay. Now, to make things more complicated, we can go ahead and create another version of this. And I'm actually going to copy this table. I can leave it up here. I've got room. That's fine. Okay. There is another more formal way to represent a state machine. So this is pretty informal. I mean, it contains pretty much all the information you need. This is very formal way of doing it, but there's a way to represent somewhere in between these two. And this is called a state machine chart. Now, these are going to be useful because they get used less in digital logic realistically, but all the time in software. So if you end up working on software, collaborating with someone in software, they use this kind of state machine chart all the time. And what it does is it's the same kind of idea where we're going to have this state 0, and we're going to have an entry point, but we're going to break out the decisions so that when I enter state 0, I come out and I make a decision. This means I'm making a decision. What am I deciding on? I. Is it true or is it false? Now, this doesn't have to be I. This is just our example. We could end up writing something like X1 is my decision. Well, what is X1? X1 could be something a more complicated expression like A and B or C. If I had 3 inputs, and I would just have this written as X1 because I don't want to write A and B or C in a little box. So, well, we have just I. And then out of I, you just put 2 arrows that are going to come out. You can use any of the joints, whichever tends to be easiest. And if I have a 0, as I said, we stay put. So what happens is we're in state 0, I compare I. If I is 0, we'll wait and check again. On the other hand, if I get a 1, we want to go to state 1. State 1 is going to make a decision. Not every state has to make a decision. Sometimes I could do that. One of the things that we can do is if this is a more state machine, the reason is maybe this is, I'll just leave it the way that, or with an output of Z. And this is back to 0. So all I'm doing is for 1 clock cycle, I'm asserting Z and then going back to 0. Why would we do something like this? What's an example that you guys are doing? What do you do in the stop state that would make this kind of signal? Yes, the ready, right? This would be a way of making it so a ready flag, saying that your data is ready. It comes into the state, says, I am ready, moves out. I don't want that ready flag anymore because now I'm updating whatever that buffer is. That's why you would use something like that. Well, here, S1 is making a decision. It's, again, deciding based on I. If it is 1, I'm going to come out the other side because it's a little bit easier to draw. There. Notice that I come into the signal. I don't draw it back into the state. I come back into the connecting signal. It just continues the path. It's still clear if you do it the other way, but this is the correct way. If I get a 0, oh, and I got to label it 1, 0. State 3. Okay, so state 3 also makes a decision. It is still based on that input because it's just 0 input. There's only 1 input. We're looking for a 1, 0, 1. So I've gotten the 1, 0. Well, our output 1 is going to assert true. And then it takes us back to state 1. So state 1 is here. What that means is I've built a Mealy machine. So instead of doing the slash output like you do in a more, I create an explicit output bubble. If I get a 0, I start all over again. Okay, those are SM charts. They tend to be more formal than your SM diagrams and less formal by a little bit than your SM tables. These are all useful things. I can easily ask a question on the exam that asks something like, build me a detector that detects the sequence 11010. Represent this as a state machine diagram, table, and chart. Right? Very possible test question. When I ask that, make sure you don't screw up the diagram, because messing up the diagram will make you mess up the rest of it. Okay. We are at, well, let's, I just want to kind of hammer home state machines because they're just so important to everything that you're going to design in digital logic. So I'm going to do a couple of other examples. But before I do the next example, the thing that I would like to bring out is that there's this idea of linked state machines. Now, linked state machines are really important because you're not going to build your whole system in one state machine. And you're going to see this firsthand because we're going to start lab 2 this week because you've all totally finished lab 1, right? And lab 2 is going to be a transmitter. Okay, so you've built a receiver. The PC, you push a button, it's going to send a letter out, and it displays the binary along those lights of what letter it received. Lab 2 is to build the transmitter and then turn it into a loopback system. So that when I push an A, it gets an A, sends it back to the PC, and it displays an A in the terminal. Okay, this is nice and simple, but these are linked state machines. The signal that we're linking them is ready, right? So that it knows when it got that data, it is now ready and can send it back. At least 10% of you, probably more, are going to build your state machine and it's going to sit and you're going to push A and it's going to send A 100 times or something like that because you built your state machine wrong. But let's start with the this is your receiver. Now this can be confusing. So I'm going to talk about it from your guys' perspective, right? Because the PC also has a receiver and transmitter. I'm going to talk about this from your perspective of the receiver you built. So it's idle, start bit, data, and then maybe stop bit, maybe not, but let's go ahead and do it explicitly where during the start bit, it's going to output ready. Okay. This is a very simplified state machine diagram because I'm not explicitly labeling when things happen, right? So to do this, I would need to say not S data. The transition from start bit is essentially not well, I'm not going to call it timer. What are we using for this one? Countdown? Well, half count is the variable that we're counting down from. The counter that we actually use is, I think, countdown or big count, right? There's two different ways of expressing it. I'll go with big count, right? Because our little count is going to be our bit counter. Big count is our timer that divides from 100 megahertz clock down to a baud rate of 115200. The reason I write it as not bit count is because I'm going to count down from some binary, right? And eventually I'm going to end up at 0000. And so this is just not a vector, right? We can't write this in the if statement because our counter is an integer and not a vector, a bit vector, but the idea is valid, okay? Not bit count, I go to 0. Now, again, I could go out and say a whole bunch of things. Well, when there's an idle, I would need to technically say in idle, I have all of these outputs where bit count equals half count. Actually, that's really confusing, isn't it? Because BC is big count and bit count. It's a terrible decision to make. Let's fix it. I'm just going to use CD for countdown. Okay, what other signals would I need, right? There's a bunch of other things that I need. Ready is 0. Bit count is 7 if you're counting down, and so on. I have this whole list of things in here if I'm making a complete diagram. Anyways, this main is not CD. This one is not CD and not bit count. Is that transition? And then start bit is just not CD. Where inside of data, we initialize CD to half count. Now, in these complicated state machines, the reason I don't write all of them out is because this is a little bit confusing, is because technically, this isn't really when it happens, right? It's not we're not assigning CD to half count all the time. We're actually doing CD as half count out here. Right? It's in that transition when I leave and go there. So we kind of have this weird hybrid mealy/more. Right? It's a little bit messier than we like to talk about it academically. We like to talk like, oh, it's strictly mealy or strictly more. You get hybrid all the time. That being said, on an exam, I'm not going to trick you with a hybrid like state machine table because that gets really confusing really quick. So this though is a little confusing. All right. This is our core state machine. This is our core logic, but there are linked state machines to it. Okay. For example, a countdown can be a state machine. It can just be a bunch of shift registers too, but you could design it as a state machine, right? And that state machine might do something like, well, we are going to have, sorry, I didn't write this one out in my notes. Now I have to think about it for a little bit just to make sure I do it. It only needs like 2 states, right? Because we're going to have initial, which we're going to just call S for start. And then we're going to have another state that's countdown. And then all that happens is, actually, let's do 2 different ones because this is a viable way of doing it. Okay, I have half count and I have full count. This then comes from some initial state that is going to be my start. Okay. That's my decision. If half count is true and not full count, this is if full count is true and not half count. This is getting decided from this state machine. So these are 2 input signals, half count, full count. That means here when I initiate the signal countdown is half count, it sends it to this state machine. It says, oh, look, half count. Set that value, come to countdown. Countdown then just simply says count -1 if, right? So that's all this is doing. See that's in here. I'm sorry, C -1, right? C -1, and that's if CD. But if not CD, meaning we hit 0, we can go back and wait for the next, hey, start counting signal. Now, you didn't build yours this way, most likely, right? You probably just build it inside of the state machine. But this is a perfectly viable state machine that would do counting down. And instead of sending the exact value, you're just sending a binary value to another state machine. Here, not only am I going to say CD, I'm going to say not CD with an output signal of switch. So then, instead of having not countdown here, it's just waiting on the switch signal. Right? That's linked state machines. Well, you're going to go ahead and you're going to have another linked state machine that you're actually going to have to design, because you don't have to design this. This is fine. This is just an example. But you are going to have to go design something for your transmitter. And it's going to have some series of states that it's going to jump between that I'm not going to give you the answer to, because I already did that with this guy, right? Baby steps. So first I give you this basically, and now you're going to have to puzzle this out. But you're going to have some state really idle here that is just hanging out until really hard to write at this angle. Okay. Ready. Right? So when this guy asserts ready, this state machine can now leave idle. So there is a link. If you went and looked at the book, they would have it, they would probably take the time to draw this with more planning, but it would have like this dashed line. Have a link saying that state depends upon the output from another state machine. Now, it may not surprise you that you're actually going to have a whole bunch of linked state machines by the end of this one. Right. So we're going to lab 1, lab 2, all the way. I think there's 6 labs, and lab 6 is really just integration. It's really the step of taking all of your state machines and putting them together. Because we're not going to leave off with an echo back. That's boring, right? That doesn't do anything. No, what you're going to be doing is you're going to be generating data with the digital to analog converter, measuring that with an analog to digital converter, filtering that through some data processing techniques, and sending the results to the PC over your UART. This is all going to be initialized by typing commands on your computer. That's where we're going with this. So it's all going to be these heavily linked state machines. Okay. Now that I've got that out of the way, okay, so I'll say this up front. On the calendar for today, if you're paying attention, I've listed this thing called microprogramming. Microprogramming is, it might be worthwhile to go read in the book, especially if you're like interning and doing something like PLCs or something. Because microprogramming is basically using this SM charts with a couple special conditions, with the main one being that it can only ever make one decision per state. It only does one comparison. So the only output that it ever puts is a next state true or next state false output. It's just, do we go to the next state? Now, microprogramming has this really nice feature of it's very simple to program. It's very easy to debug, but it takes a little bit more memory than some more optimal solutions. That's really all I expect you guys to know. I think if I decide that it's more valuable, or if I go look at the ABET accreditation requirements, you actually have to know it, I'll go throw it back in. The last semester I taught it, well, I guess a year ago, I didn't really find any value for it in the students. So I'm kind of just dumping it so we can spend more time on things that are going to be more relevant to you. But if you're working with PLCs in your career, or if you want to end up in industrial automation, it's probably worth at least going and reading the microprogramming section. I think it's like 5.5 or 5.6. But instead, we'll do something a little more fun. What we're going to do is we're going to build up a state machine for the game of craps. Anyone know craps? Man, kids these days. All right, craps is a dice game. You take 2d6. If you're not a nerd, d6 means a 6-sided die. I'm a huge nerd, by the way, if it wasn't obvious. So you take 2 6-sided die. You roll the dice. If you roll a 7 or 11, you win. If you roll a 1, 2, or 12, you lose. Anything else, that's your new goal to try and roll. So say I roll a 4, I haven't won or lost yet. I roll again. If I roll a 4, I win. If I roll a 7, I lose. Okay, that's craps. It's just a simple gambling game. You'll find craps tables in any table in Vegas. I'm not really a gambler, but you know, back when I was a teenager. So we can start describing the state machine table just by understanding, state machine diagram. I'm going to start with a diagram just by understanding the rules of the game. And we're going to put some conditions on this. Let's pretend that we're designing this for an arcade. Okay. Now this arcade is going to be the simplest arcade in the world because it's going to have one button, which is roll. It's like the shoot, what's that stupid board game that everyone plays when they're kids, which they have the little bubble that you push it and it pops the dice up? Sorry. No, it's like Trouble. Yeah, Trouble has this little dome where you push it and it has a little spring-loaded thing that pops the dice around in the dome. That's basically all you have, is your little bubble to push. That's going to be your roll button. Well, that's what we'll define our roll button as, is a thing that we push and it rolls for us. Difference is this is rolling 2 different dice, okay? So what I described is you win if you roll a 7 or 11. So we need a way to add the dice together. That's going to be simple combinational logic. We're going to have a full adder with inputs D1, D2. D1 and D2 are actually going to be generated really simply. They're going to be running at some clock, different clocks. They're going to have, I'm just going to call them C1 and C2. Where I have a clock. And this clock is feeding into a counter 1 and a counter 2. These count up from 1 to 6. There's a clock divider in the middle so that they count up at different rates, right? So it's one's going like 1, and the other one's going 1, 2, 3, 4, 5, 6, 2, 2, 3, 4, 5, 6, 3, 3, 4, 5, 6. Now this isn't random, and this is probably not actually legal if you were to go and try and design this particular game for Vegas, because they have to have certain criteria for randomness. But in all intents and purposes, if you were making a game for teenagers or something, this is sufficiently random, especially if they're running at 100 megahertz clock. That is effectively random for pushing the button, because you're never ever going to time the exact right point to do it, right? You're never going to be able to rig that game without getting access to the electronics. You have access to the electronics, it's pretty trivial. Okay, so these are 2 counting up. When I push the roll button, it stops this counter, right? That's how I say it. I've rolled this number. Okay, That's our state machine. So we're going to be sitting in some idle state. We're going to push a roll button. And what we want to end up, one way or another, is win or lose. Now, I'm going to preface this by I have not done this state machine. So what you're going to witness is me walking you guys through how to figure it out the way I figure it out. So what I've done is I've got my start, I've got my finish. Now I need to figure out what happens in between. So this one is going to push the roll button. That needs to take a state where we're going to just call this sum. Okay. At this point, it's going to pull in the values of counter 1 and counter 2 and store it in a sum. Now the state sum is different than the value sum, but it can be helpful just to name the same thing. It's not really that big of a problem when they're that closely related. Then the next thing that this sum does is it's going to make a decision. Now this is where this kind of decision tree can actually help you a lot if you wanted to start doing something kind of weird and hybrid-y. But let's start this way, which this is 7 or 11, which really I could do this, but that's a little bit awkward since this could be 18. So if sum is either one of those, we win. Once I win, I might have like a prize state or something. And I can come back up to idle. Lose happens when S is equal to 1, 2, or 12. If neither one of those true, now I can go to a different state. What that state does is I'm just going to call it, actually I call it SP, or set point. Yes?
This might be irrelevant, but how do you get 1 out of 2 dice?
Good question. I probably mean 2 or 3. It's not irrelevant. Okay. Okay. Yeah. Okay. What this does is it's going to assert a signal that is going to hold the results of the dice, right? And now it's going to wait for roll button. And if I don't push roll button, it's going to hold. It's just going to sit here and wait for me to push that roll again. When I push that roll again button, it's going to send another signal to this counter, right? It's going to stop it. It's going to store and then compare what we just stored into set point to that. So I'll call this just compare. And if SP is equal to the roll, which just for definition, right? The roll is going to be output of that addition. If they're equal, I win. If roll equals 7, I lose. Otherwise, hang out. I'm just going to write else rather than the whole expression.
Shouldn't the lose from the compare also contain 2, 3, and 12?
This one, no. Once you've not rolled one of these on the first time,
Oh, you only lose if you roll the same numbers twice.
You only lose if you either roll this on the first roll or 7 on any succeeding rolls.
Oh,
And this actually is not quite right because we don't sit and compare. We need to wait to roll again. And so there's probably roll again. That's what this state is. And this is already the roll button. I'm just going to hang out in this roll again state until I roll again. Well, this is our state diagram for the craps game. It gives us a place to start. Now, I've given you, you could design this whole thing without really understanding of any of this logic. I just wanted to give you guys that peek of where we're kind of targeting with this ones. Where's my notes? Okay, here we go. So we can then start building up our state machine chart, right? The more official one of doing it. Actually, what may be useful for you guys is if I put up, I would really like to display this on the overhead because it would be way faster, but the technology is never reliable, so you have to put up with me drawing for a second. Okay, so what I'm doing here is I'm building up a block diagram. This concept is really important itself, which is why I wanted to do this. Is I'm building up a block diagram of what the system is going to look like. So all I've done for now is taken that idea, which is the full ladder and the counter, and I've thrown it into this roller block, right? It has these 2 counters that are going to be fed by a clock, and they're also need roll button, which is essentially an enable, right? That's all a roll button really is if I push it, it turns off the enable. Then I have an adder, which I talked about, the full adder, which is going to store potentially in this set point and look at a comparator. So we need control signals coming from somewhere. So if you were in my 2700 class, you certainly heard this a whole bunch. If you weren't, I don't know. But there are 2 important components to any digital system. The 2 components are generally called the controller and the data path. This is my data path, right? This is where all of my data that I'm making decisions is coming from. My controller is going to send the signals that this thing needs to use. So like, for example, set point needs a control signal that we can just simply call set point, right? That tells it to either store or don't store the output of my roller. Because that signal is always going to that register. It's not like we're building a system with a mux, say, that is disconnecting or connecting. It's just always connected is just a series of these flip-flops that either store that binary value or not. Similarly, comparator is always going to be looking at the comparison between the output and the adder. It's just whether or not the output of the comparator is sending this data point EQ back to the controller or not. Right? So what I'm going to have then is the controller. This controller is going to output things like set point. It's going to have inputs for things like if they're equal. These inputs and outputs of the controller are plugged into this state machine. That state machine is inside of this controller. Generally, if your sum here, right, has this output, I'm going to actually switch colors because I didn't draw this great because I kind of squoze myself into a corner. Am I actually on the video? Because that'd be really embarrassing if I wasn't. Okay. This signal also needs to come down to the controller, but we don't feed that directly in necessarily. We want to make a decision first, where this is just going to decide, what is this, right? And is it valid? So basically it's going to do the comparison operation, but rather than between set point and comparison, it's going to do it between, we wrote this as S equals 7 or 11, right? And it's actually going to have several outputs. So it's going to have an output for 7 or 11. It's also going to have an output for 2, 3, or 12. And then those are going to feed into this controller to inform it what state it's going to be doing. So in your controller and data path, you're going to build them up as block diagrams. It's good to write this controller as one big state machine, but anything that you can move to simple digital logic that's like comparisons, additions, you know, anything combinational logic, you're going to draw it as a block. I generally shy away from anything inside the state machine that I would write as its own block. Because I could write this comparator like inside the state machine, but I don't like to do that. I like this to be strictly the state machine, rather than like the next state logic or output decoder. The other remaining outputs then is this is going to have things that it decides win, lose, which those get asserted when I'm in that win or lose state, right? Then this win, instead of having this prize state, this turns out to be unnecessary now that I've built up the block diagram. There is nothing wrong with discovering that you've done something unnecessary and going back and erasing it. Because what I could easily do is have this win statement plug into some digital logic that is connected to a motor controller that, you know, it's like a claw machine or something, I don't know. Right, it just dispenses your prize. I don't actually need the prize state. Just like in your UART, you don't actually need the stop bit state if you're very careful in your design. But anyways, some of the states are optional, but always keep track of all of your inputs, all of your outputs into your controller and into your data path. Anyways, that's that for this lecture and the representations of state machines. Do we have any questions since I have a couple of minutes? Nope. Okay, good. You're all experts then. I highly recommend finishing your state machine, your lab 1 before lab on Wednesday. And the ideal situation is you'll finish it, you'll show up to lab, you'll show it to me, I'll check it off, and we'll move on to lab 2. Lab 2 should be posted and available, but don't print it out yet. I actually need to make a couple of changes because it still refers to that 7-segment decoder, which you don't have to use for this one or that one. I'm just going to throw that out to simplify everybody's lives. So by the end of today, I will have that lab updated. Question?
So we've got one more due on Wednesday and Sunday of this week.
Oh, do we? I will double check that.
Oh.
I have it set up from my last semester that it just runs itself on that side of the homework things. And then I just go and read them to make sure that I've actually taught you guys how to do the problems. If you ever run into a problem that you don't know how to do, email me and ask a question, and I'll either say, no, you should know how to do that, or, oh no, I messed up and I missed something in lecture. You don't have to do it. So don't get stuck forever on a problem in homework or in lab. I don't want you to get stuck forever. The labs are designed to prepare you for real life industry. The homework questions are basically to supplement that and make sure that you understand the theory of how this digital logic works. Right.
Frozen for a moment. I changed my copies and now it is still frozen, but after a few seconds you will set it itself.
Really?
And I start working again when it's itself. I also programmed one of the switches to be reset, and when I use it, like it keeps my last value, but every I don't know if I should make it go back to 0 on all the lights.
No, you shouldn't make it go back to 0.
The light, if it's frozen on
So
A,
this-
this reset, it keeps showing A.
So you're not wrong for this lab. It's not necessary. It's just a problem that you need to be that could be coming up. And next lecture, I'm actually going to be introducing debug cores, which will allow you to look at the signals on your FPGA and hopefully diagnose what's happening. So that'll be something you'll have to do for like the as part of lab 2 is figure out what's happening and going wrong.
One last thing, my ready is being inserted for the whole idle time. Is that okay?
That's horrible. Yes.
Okay. I'll fix it.
Ready should always be 0 in idle, because otherwise what you're saying is you enter idle and now the data's ready, which is not true.
A quick question on the homework test tonight. One question that I'm not sure if you taught it or not, but or I just forgot it. It says that there is an equation that y is equal to a XOR b.
Yes.
And it says put that into a process sensitivity.
Yes.
And I don't know how you do that.
Oh, you remember when we say
Like,
something like process on clock?
yeah.
Well, when we process on a clock, if we do rising edge, this makes it sequential logic.
Is that idle?
Similarly, if I have an XOR gate, like so,
Make it on the circuit. Just
this,
ready.
anything I do in here, because I have all of the inputs in the sensitivity list, this is just sequential logic.
Okay.
So this process,
I have to look at it. I'll look at it.
and then
Oh, okay.
I built that gate.
Okay.
It only works as sequential logic if all of the inputs
Yeah.
are in my sensitivity list.
Okay. I thought it was saying to just make it so your process just has a sensitivity list, but will assign C to A, X or B, like without having
Oh.
it be just like in the process. So
Yeah,
that's what
yeah,
it
no,
says.
it's just this.
That was
Okay.
from, yeah, you in the book, have an example.
Okay.
Specific.
I figured. But, all right, cool.
Question.
Yeah.
Are you gonna be?
I overthought it. When,
I will be recording all of them. I don't let students in live because I don't like juggling that, but I will be starting to post all of them
Okay.
generally. It's not 100% guarantee. If it screws up, I will post a reading chapter kind of thing to go read.
There's a chance that we can go back and watch the class. Is that-
Yes, absolutely.
Okay.
Speaking of, I have to go tell this to stop recording.